Okay, Rishi making you a presenter.
Yes, sir.
All right, go ahead, check please.
Oh, yes, sir. I can present. Okay, guys, is my screen visible?
Yeah. Okay, so
Okay.
everyone who's possibly missed out the first particular lecture, we completed Integrator using LTspice. All right. Currently, what Rishi is going to be explaining you all is the Integrator itself, however, with Orcad. All right. So this is another tool that, of course, our lab has a license of, and that's the reason why I thought that even this is a particular tool that you all can use. Again, at home, if you're using a crack version, please do not use it. Okay, this is being taught specifically so that when you come to college, all right, and if your system has a Orcad license on it, all right, you can use Orcad also to do it. Orcad is a much more stronger version of LTspice. All right, so PCB designing and something is also something that you can do with Orcad. All right, so uh, when you move in the scheme of things, you start off with LTspice, you move towards Orcad, and industrial PCBs are designed using something called as an Altium designer. All right, so there'll be a set of people who will again come up with Altium and who will be teaching you all Altium and PCB designing. All right, so I'm currently working on that to get a set of people who will also teach you all Altium. All right, for PCB designing, but the reason of also Rishi coming in is so that specifically they can show you what other tools are available. And again, Orcad is not a free open source tool. All right, so if all of you all know, you normally get an academic license. LTspice is an open source tool completely. So that's the reason why first preference in an academic setting is being given to LTspice. All right, Rishi, over to you, please.
Yes, sir. So you guys may like Nidhi and Nandini a little bit, but you guys are going to hate me because I'm going to be the one who's making you do it on a second software. So I'm just coming in accepting that from the get-go. But coming to ORCAD, just a little something from my side beyond what Mayur sir said. Over the last few semesters, our batch has hated using multiple software tools, but the fact of the matter is that as I write my CV right now for my admissions in the future, I find myself putting in all of these softwares on my CV. And if you're going in for an electronics degree in the future, or if you're going to go into an electronics related job, you are going to have to use several softwares and maybe softwares that you don't know or don't like. So knowing multiple softwares and knowing how to move to a new software very quickly and getting used to that is going to be a valuable skill for you no matter what. So moving on to ORCAD, I hope all of you have installed this already because I think the install files have been put up almost 3 to 4 weeks back. So if you have it installed already, all you need to do is you can go to the location that I've specified here on screen. This PC, OSC, Cadence, SPB 17.2, Tools and Bin. And within that folder, you will find something called capture.exe or capture application. And that is what we will be using to run ORCAD. So for me, at least this works. I can just type, I can just type capture into my Windows start and it opens for me. So here I am. I have opened ORCAD. It takes a little time to just start up, but give it that, no issues. Once you're in ORCAD, what you need to do is you need to click on the button for new project. Ensure you do not click new design because this is generally for this thing, PCB schematics and things like that. What we want is a new project. Keep the PSpice analog or mixed A/D selected. And here you can give your name. So what I'm going to put it as is practical integrator. And then for the location, what you should do is you should go into browse, go to your desktop or whatever folder you're using. And this is where you need to be very particular from day one. Have folders for every subject. Within those folders, have folders for each experiment. So I'm going to name this experiment 3 integrator. And this is because you're going to be doing practicals for 4 to 5 subjects in the coming semesters, and you're going to have 10 practicals or so for each of them. So ensure that you keep all your files organized from day one, or it's too much of a pain. So once all of that is done, you can click OK, and then click on create a blank project. We don't want to start with some sort of preset. We want to start with a blank project. So here we go. Give it a second to load, and you should see the same screen that I am seeing. You guys can try to follow along with me if you want, but if not, I'm trying to be as thorough as possible so you guys can watch the recording again later on and do it that way. All right. So in order to create an integrator, what we're going to need is our op-amp. So one good thing about Orcad that I love is that all of the op-amps that you need are already going to be ready. So I'll show you what you guys are going to see when you start Orcad up. What you need to click is this button over here called Place Spot. When you click that button, you will most likely see a screen somewhat like this. Now, the issue with this is none of the libraries of Spice models is already installed in Orcad. So what you can do to get all those libraries is click this button for Add Library. When you click that button, this is the screen that you will see. You'll see the PSpice folder with several different libraries below that. So all you need to do is go into the PSpice folder, select any one library, click Control A, and click Open. So if you do this, you can see that all the libraries that we need are now imported into Orcad, and we can get going. So now within this place part menu, you can just type in any op-amp that you want. For example, I can type in OP07. And you can see here that we have multiple versions of the OP07. The OP07C, the OP07CS, D, E, and even just the OP07/opamp. And you can see the symbol here. Similarly, you can see the LM3 to 4. You can see the LM741. You can see the TL084. So you have all the op-amps that you need right here. Now, I like OP07 for its particular simulation characteristics. So I'm going to be using that. But you guys will probably have to do your experiments with multiple op-amps. So be ready for that. All right. So now once I have placed my op-amp, I just have to double click on OP07 here in the menu. And this will come up with my mouse button. And I just have to click once, left click once to place it. And then if you want to delete a component, all you need to do is click on the component, press the delete button. One good thing about Orcad is that you can move components around really easily. I can just drag and hold on the op-amp and I can move it around. Now what you'll notice is that the positive or the non-inverting terminal is situated above and the inverting terminal is situated below. We don't want this as we're used to the other convention. So all you need to do is right click on the op-amp. Yeah, right click on the op-amp and just do mirror vertically. Just press the mirror vertically button. So that sorts your directions and polarities out. Now, in order to actually build our circuit, what we're going to do is we're going to start by placing a few resistors. In order to place the resistors, all you need to do is type R in the part list in place part, and you can see that R analog has come up. So we can just double click this, and we can place the resistors exactly where we want. Let's say we place one here, we'll place one here. There'll be a capacitor on top of that, and we'll place our ROM somewhere here. So these are the resistors that we're going to need. Now what we need is our voltage sources. So we'll obviously have our alternating current sine voltage source, which will be our Vin. But first we need our DC biasing voltage. To get that, all you need to do is type VDC, and you'll come up with this called VDC/source. And you can just connect them here and here to the V plus and V minus terminals. Now you can do what has been done in LTspice with the label creations and everything. But I don't know, I just find this to be much simpler, so I do this. But if you guys want, I can cover it in the future practical as to how to create the labels. Okay, so now I want to ground both of these VDC sources. So all I'll do is click this button, place ground bracket G. I click that once. I select the 0/capsim, the 0/capsim variant, click OK. And here I have a ground in my hands. Now, I clearly can't place this here directly. So what I'm going to do is I'm going to rotate this component. Similar to LTspice, you can just press R here, or maybe in LTspice it's Control R. I can just press R here, place one up here on the VCC, place one down here on the VEE. So there we go. That's our ground up. Now I can see that this resistor is awfully close to the ground. So I can just drag and hold and move it a little bit. Nothing, no sweat there. All right, now we need to place our voltage source, our sine voltage source. So what we're going to do is we're going to start with V sine, and you'll come up with V sine slash source. Double click on that, place it about here. That should be fine. And there you go. That's your sine voltage source done. I'll cover the other voltage sources in due time. Now we're free to connect up our circuit. So you can just click this button here called place wire. Since this is an industrial software, there are shortcuts for every button. There's P for place part, W for wire, G for ground. But you can just click the buttons if you're not comfortable with that. So we can just wire all of this up. No issues here. Pretty simple. And this can go down to my ground, and so can this. You can use just one common ground for everything. That's completely all right. I like to keep my circuit clean. If not, you can always place different grounds. There's no issue there. Now, I don't like the way this looks. I'm just going to move my ground down a little bit. We'll delete this extra wire, and there we go. My circuit looks pretty clean. All right, now all we need to do is give the values for our resistors, and oh wait, I'm so sorry, I've missed out on the capacitor. So to place the capacitor, all you need to do is just press C in the place part space, and you can get your C analog right here. I'm just going to place it here. And again, I can wire this up the same way that I did the others. There we go. These are all our components set up. Now we just need to give them all values. I'm not going to go too much into detail for this, but we can give them values based on the calculation shown here. What I'm going to be using, a 4.7 nanofarad capacitor with 33 kilo ohms and 3.3 kilo ohms resistors. And as you can see, the ROM calculation done here, it gives us approximately 100 ohms. Again, Nandinee showed you for multiple values of capacitances, and I believe all of you should try different capacitances and values. So that'll help identifying your circuit as unique, because when 60 people are doing the practical, it's easy for everyone to have the same values. So try different values and make sure you do that. And one key Nandinee mentioned earlier is the standard value of resistances and capacitors. So this is a short table of resistances you can see with standard values. And beyond these values below 1000, you'll notice that all of them are just multiples of 10 and powers of 10 of the previous values. So when we're doing simulations on softwares, it's very easy to just use values that are really convenient to us. And we have that luxury here. But the moment you move to in-person college, which I know probably none of you want to, when you do that, you're going to have to get used to using resistances and capacitors of very specific values. So you have to get used to combining maybe 4 different resistors to get the resistance value that you want. So it's best that you get used to that, right? So we're going to be using these standard values. As you can see, 33 is a standard value. So that means we're going to have 3.3 kilo ohms, and so we're going to have 33 kilo ohms by extension. Right. So now we can move back to our circuit, and we give all of the values that we want. In order to do this, all you need to do is, you can see this one end here, right? Just double click that, and this display properties table will come up. And you can just backspace everything here, type 4.7 nanofarads. You don't even have to type the farads. I just like to do it because it looks cleaner. And you can click enter. That's done. Then what you can do is you can double click the resistor value here and type 33K. Double click the R1 value here, type, I think it was 3.3K. Double click the 1K value here, type in 100. So we're done with the resistors and the capacitor. But one key thing that's remaining is the DC biasing that we have to given. You can just double click that, type 15 volts. Double click that, type 15 volts. So that's our biasing set. Okay, now one thing that you can do is you can also rename these components. So for example, I double click R3 and I type in ROM. Okay, this is already R. I think I can name this RF because it's going to be RF by R1. And if you want, you can always rename this as a CF if you guys wish. All right, there we go. So these are all our components set up. Now it's time for us to give the input voltage. So using vSign, you have these four input places to give input. Our V offset is going to be 0 because we do not want any DC offset voltage. Our V amplitude is going to be, let's just give it a 1 right now, and we can see later what other values we can give it and how we can change it. Frequency, let's start with 1 kilohertz right now, but we will check out several different values. Again, you don't have to type hertz, you can just type 1K. The software is smart enough to figure that out. And this AC thing, you can just give it a 0, as this will be of no use to us. Sorry, there we go. All right. Also, one good thing in Orcad is that you can easily move around these labels as well. So if you're trying to get a good screenshot for your PDF, it's much easier to manage that completely. And since I'm here, I'm also going to run over one more thing. I can go into place up here. Okay, the place button that you guys see. And there is this button for text. So I can just click text here. And I can type in my name and SAP ID, which is something you guys are going to have to do for all your practicals. So there you go. That's my name and SAP ID. And I can just place it here. All right. So there we go. That I've identified my circuit. Cool. So now that our circuit is ready, we are almost ready to go simulating. I'll just close out this part placing thing. Okay. To simulate the circuit, what you need to do is you need to go into the LTspice button up here. The LTspice button, and then click New Simulation Profile. But before I do that, one good habit, I am just going to save my circuit because I have lost way too many circuits in the past. There we go, I saved it. And when you get New Simulation Profile, all you need to do is type in a profile that you want. Let's say I'm going to do test integrator. You cannot have spaces in the simulation name, so don't bother wasting your time trying that. And there we go. Give it a moment, and you will come across this screen. So setting up your simulations in Orcad is much easier than in LTspice. Thank God. That's why I love this software. You have text boxes for everything that you need, and there are drop-down menus, things like that. Seems luxurious as compared to the previous software. Anyways, so what we want is a time domain transient analysis here, of course, as you've seen on LTspice itself. And these are the different options you have here: DC sweep, AC sweep, and bias point. We will be using the AC sweep at some point, but as of now, we just want a time domain. And for now, let's just set this to 100 milliseconds. We want our total runtime to be 100 milliseconds, let's say, and our step time to be 0.01 milliseconds. I'm setting this actually, you know what? I'm going to set it as 1 milliseconds, and you can see what happens later on. I'm going to click apply. I'm going to click OK. All right. So in Orcad, what you do is you give your terminals, like the terminals to check voltages before you do the simulation. So I can just click this V button here with the I don't know what it's called. I'm blanking on it, with the terminal. I can just place one right here at the input. Again, you can rotate this as much as you want. I can place one here. Okay, Orcad is lagging a bit, and I can place one right here at my output terminal. And there we go. My SAP ID is wrong. It doesn't matter, but I'm still going to correct it. There we go. Yeah. So now we're ready to simulate this circuit. In order to do that, you just need to click this Run LTspice button right here with the play button. So I'm just going to click that. It's going to take a little bit of time. It's a big simulation. And if you can see, this window down here must have opened up. And if I just click that once and I full screen it, there we go. We can see the simulation. Obviously, this is a little hard to see because of how big the simulation is. So what I can do is you can see the this thing here, the x-axis. I hope the colors are visible. If it's not, please tell me. It's easy to change that. So actually,
no, visible.
Okay, it is okay. I'm glad. So I can just double click the x-axis right here. I can go into x-axis user defined. So currently the range is automatically set, but I can go and make it user defined. And I can make this thing 10 milliseconds and click OK. There you go, done. And now you can see that we don't get a very fine output, which is pretty bad. We don't want something like this. And that is because we're taking very few points in our output. So you can go into the simulation button up here, click on Edit Settings. wait for the window to pop up. And let's say, let's make this 0.01 milliseconds, just because I want to torture my laptop. And what I can do is I can make this 10 milliseconds instead of 100. Click apply, click OK, and then go back in the simulation and click the run button. And there we go. We have a much finer output. You can see this small sine wave here as our input voltage, and you can see this bigger minus cos wave here as our integrated output. So you can see that there is a phase change happening here. And that is obviously because we're, first of all, putting our input at the negative terminal, at the inverting terminal. And secondly, because this op-amp is not ideal, there will be a certain slew rate. And if you guys know what slew rate means, it's basically the op-amp's delay in reacting to input changes. And that will increase as we go on to higher frequencies. All right, so at 1 kilohertz, that's not an issue at all for us, almost. Right, so we can see here that we have a 2-volt peak-to-peak input voltage, and that is 1-volt peak. And we can see that the output value is going all the way up to 7.125 or so in amplitude, and about 14.25 volts in peak-to-peak. And that pretty much matches with the output values I have right here. I had plotted this in my third year, so you guys can just take a look at this table. So here are my values, the input values that I've taken. Here is the 1 kilo ohms value that I've, 1 kilohertz value of FA that I've taken. And you can see these are my output voltages. Now we're just going to try this quickly for a few different frequencies, and then we can move on. I'm just going to cross this out. I'm going to go back to my frequency. I'm going to type 100 hertz. Let's just type it as 100 to show you guys that works as well. Click the play button. The window pops up, give it a second, and there we go. So it's pretty easy for me to just increase the simulation here. I'll just make this 100 milliseconds, apply, okay, simulation run. There we go. So we have pretty much 10 volts. If I go into the nitty gritty, it'll probably be 9 point something. But you can see it as 10 volts up here. And you can see that we have still our 1-volt peak to peak. So here we're getting the ideal gain of a normal op-amp. It's the op-amp is not working as an integrator here, right? So now we can go back here, and I'm not going to show you the 100 to 1000 frequencies, but you have to plot it at an interval of 100, as Sir said. What I'm going to do is I'm going to test it at, let's say, 5K, and then we can quickly move on to 10K. Right. So as you can see, okay, that is a disaster. I'll just okay, I can just reduce it from here. Pretty easy. User defined. Let's make this 5 milliseconds. I think 5 should be enough. Yes, it is. Okay. So what you can see here is this wave right here, this first wave right here. There's a certain delay because it takes the capacitor a little while to get charged up, as Nandinee said earlier. And I'm going to actually reduce this further. I'm going to make this, let's say, 1 millisecond. Okay, there we go. So you can see that the phase change here is slightly different as compared to what it was for 101 kilo ohms or 1 kilohertz. And that is because as the frequency increases, it's more and more difficult for the OP07 to keep up with the input changes. And that is because of its relatively low slew rate as compared to maybe some better industrial op-amps. So you can see this here. And you'll be able to see this as a fair difference amongst all the different op-amps that you're testing. So keep a mental note of that. Now, one key thing that you
Rishi,
guys need to know.
Just one sec. So what you said is exactly right. I want you to test the slew rates for this particular op-amps, all right? When you're looking at TL084, when you're looking at 741, and when you're looking at OP07, you'll observe this slew rate response being completely different, and because of which the phase being completely different when you're testing it with the 3 op-amps. Right? Yeah, go ahead, Rishi, please.
Yes. So one thing that you can do to sort of spice up, no pun intended, your outputs is you can go into tools, the tools button up here, go into options and go into color settings. This color settings. And this is where you can change the background of your outputs. For example, there we go. I made it white. It's a bad decision because my colors are already I am using, I think, a teal blue. So I can let's say I can make it blue. And there we go. It looks horrible, but this is a good way to change the output and input waveform colors as and when you need. because again, you are going to have to differentiate your waveforms from the other members of your patch. And here I can change my foreground to, let's say, where's white? Oh yeah, there we go. I can just make it white. I can make it white there if I want, but I prefer red because it helps me look at the waves more clearly. So there we go. So that is what you can use to differentiate your outputs. And another thing you can do is you can go plot, label, and text, and you can enter your name right here. Yeah, this makes it a little harder to copy, but I guess that's the point. So you can just plop your name on right there onto the output waveform. You guys are going to hate me, but yeah, I insist that all of you do this. All right, so there you go. That's your output waveform for 5 kilohertz. And I can quickly move on to 10K. And we can just run the simulation again. So I'll open this up and, oh my God. Right, I'll just go back into user defined and I'll make this 1 millisecond. There we go. So you can see that we're not getting a very fine output because at such a high frequency, the op-amp finds it, we don't have a fine enough output. So what we would have to do is we would have to reduce the step size even further. But I think you guys get the point. And you can see that there is almost no gain. So if you look at the peak-to-peak value of our output waveform, which is this, the one that is lower, it goes from about minus 1.35 to minus 1.4 all the way to about 0.4 or 0.6. So you're getting approximately a 2-word peak-to-peak waveform. As you can see here to the right, it's pretty much matched up. And that's because your gain is almost going to be about 1 or 0 decibels when you put it onto the logarithmic scale. All right, so this pretty much covers this section of the practical. But now what we can do is we can move on to testing it with this thing. We can test the frequency response. So I'll obviously be testing the different input waveforms, such as the square and the pulse, the square and the triangular waveforms. But for now, we can just delete this right here. Go back into your place component graphic here and type VAC. All right, I'm sorry, guys, if I'm going a little fast, but since this is the second hour, I have to go a little faster. And you can just watch the recording if you want to see everything I'm doing again. So I can double click on VAC and I can put it right here. Okay, I'll delete this extra one. Sorry for that. And yeah, you'll notice that this does not have any of the frequency inputs. That's because we just want a simple alternating current waveform. So yeah, 1 VAC is fine for us right now. And okay, this themes window is in the middle. This is annoying. Hold on. Okay, wait, this isn't moving. I need to just change the, yeah. Okay, there it was. So I can go into PSpice here. And what I'm going to do is I'm going to create a new simulation profile. Because this time we want a frequency response. So I'm going to just type freq response, bad name, but okay. Yeah, here we go. So this time we do not want a transient analysis. We don't want to run it in the time domain. We want to run it in the frequency domain. So what I'm going to do is I'm going to go into AC sweep / noise. I'm going to keep this logarithmic. I'm going to keep this decade. And Nandinee has already shown you how it works with octave, but we're going to keep it as decade. I'm going to make the starting frequency 1. Do not start with the starting frequency of 0. It does not work. At least it did not work for me. So I hope you guys don't have to go through that. And I can make my ending frequency 100K. I can, let's say, put it as 20 points per decade. That's completely all right. And apply. Okay. Right. So now we can move on to check our frequency response. And I can just click play. Oh, one more thing. Every time you set up a new simulation profile, all the probes, right? That's the word I was looking for. The probes that you've placed for voltage, current, etc., are going to completely disappear. So make sure you put your probes after you set up the new simulation profile. Right. So clearly we have nothing here. So I can just close this and I can put my probe on the output voltage because that's all I want here. And I can click play. So yeah, here we have our output waveform. And as you can see, the gain, or at least the output waveform, starts with 10 volts peak to peak. And sorry, I don't think that's peak to peak. I think that's just one way. And it moves down, and you can see that at 1 kilohertz, yeah, it's dropped quite a bit, and you're down to about 7 volts. Excuse me. And at 10 kilohertz, you're down almost to 1 volt, which is perfectly in line with what we have already seen. That at 10 kilohertz, there is almost no gain. So the output waveform is equal to the input waveform, just with obviously a phase change. Because for an input sine voltage, you're going to get a negative cross voltage on integration. But now what we want is we want this in the decibel scale. In order to get that, what you can do is you can see this V bracket U1 colon out. That's basically the voltage of the op-amp at the output terminal. In simple terms, that's just me reading out what this is. You can double click that. Once you do that, here you have the trace expression. So what you need to do here is type dB in capital, dB, open up one parenthesis, and close the parenthesis after the entire expression, and you can click OK. When you do that, this is the graph that you'll be getting. So you can see that we have 20 decibels of gain here. Okay, this is in the decibel scale. We have 20 decibels of gain here. And we have at 1 kilohertz, we have about 17 or so decibels. Can't see it clearly here, but that is the value. If you zoom in and you check, that is what you will see. Wait, just a second. I actually can zoom in. I can zoom into an area. There we go. So you can see that it is around 17 decibels or so. And that is, we have our 3 decibel drop that we were talking about earlier. At 1 kilohertz, at your lower cutoff frequency, you will see a 3 decibel drop in gain. And you can also see that per decade, we have a drop of about 20. So if we look at 1 kilohertz, we can see that we have a gain of about 17 decibels. And at 10 kilohertz, we see this perfect gain of 0 decibels. And that is because I'm just going over this in case you don't know it, just in case. Yeah, if we look at this, here is our gain in decibels formula. The decibels are equal to 20 times log of V2 by V1. So obviously taking a log of 1 by 1 is going to give you 0. And that is why we have our 0 right here. So this is your frequency response. And I'm just going to try to show you guys the phase response. I was having some issues with that yesterday, but I'm still just going to try it out. Instead of dB, I can type in P and I can type in OK. OK, there we go. It does work. So you can see our phase response in degrees. And you can see how the degrees are continuously changing. We're starting with a perfect 180-degree phase change. And as we move on beyond 1 kilo, actually even beyond 100 hertz, the phase drops significantly. And at 100 kilohertz, we see a phase change of just 80 degrees. So this is what your phase response is going to be. All you need to do is, instead of the dB, put in the P over here. And you can put in the dB if you want to see the phase frequency response. And if you want to just see the simple vanilla output voltage, you can just see how it varies with the frequencies. So you can plot all of these graphs yourself now. All right. So I can just cross out my simulation now, and I can come back to the circuit. What I want to do now is I want a square waveform. So I'm just going to delete this. I'm going to delete the VAC, and I'm going to show you how to get a square wave. So what you need to do is you need to go into the place button up here. Okay, go into the place button, go into PSpice component, and you can click the search button here. I don't know why Orcad hasn't made the V square easily available, but you can scroll all the way down, and you will notice, hold on, why is V square not there? Okay, there we go. So you can just search for V underscore SQ here, and this V underscore square part will come, will pop up. Double click on that, and you'll notice this this abomination pops up, and you can just place it anywhere on your circuit. Press escape, close this, and we're good to go. Now I'm just going to delete this extension of the wire as there's not enough space. And there we go. I'm going to place my square wave here. Just move this a little bit to the left so that we have some space to look at the details. All right. Now we need to set up our square wave. In order to do this, we're going to first look at the offset and the amplitude. Now the amplitude is gonna, so it works a little weirdly in Orcad. The amplitude is going to be like the positive side of your voltage, and the offset will be the negative side. All right, so we're going to set this as +1 and -1, so we get the square wave. I'm going to set the period as 1 millisecond, and yeah, the rise and fall times are perfectly fine as they are 1 micro, 1 micro. We do not want any delay whatsoever. Then I'm going to go into my PSpice new simulation profile. What I want is, yeah, I want the test int profile, and I'm going to say square. I'm going to call this square. There we go. All right, since I inherited the settings from the integrator simulation profile, I already have my settings set up, and I can just click apply. Okay, I can put in my voltage probes. There we go, add the input and the output, and I can press play. So let's see what we find here. All right, so I'm just going to full screen that. Okay, now we can take a look. So first of all, you can see to the left that the scale is very highly off. So I can just double click on the y-axis, make it user defined, bring it down from -10 to +10 volts. Perfect. The x-axis is a little too much for us, so I can bring it down from 100 milliseconds to 10 milliseconds. Simple. And here, perfect. You can see that we have a 1 volt peak-to-peak square waveform. And you can see that we have a sawtooth wave generation. So this is what we actually want is a triangular wave generation. But what we are seeing here is a sawtooth wave generation. Basically, it's a triangle, but it's not perfect. It's the exponential rise and fall that Mayur sir spoke about earlier. And as and when we change the frequencies, we will get a more sort of a triangular wave. And we can just test that out pretty easily here. I think we can just make it from 1M to, let's say, 0.1M. Just multiply the frequency by 10. And I'll just click play and I'll wait for my output to appear. Okay, so that took a little bit of time. Okay, so one thing you can see here is, again, okay, I'm just going to change my x-axis a little bit. I'm going to make this, let's say 10, I'm going to make this 5 milliseconds. Okay, 5 milliseconds is also too much, so I'm going to make this 1 milliseconds. There we go, much clearer. So you can see that, first of all, the capacitor takes a while to charge up. But once it does, we can see that we have a much crisper triangular wave, almost perfect, not quite, but almost perfect. And as you increase the frequency further, as you go from more of an amplifier to a perfect integrator, you're going to see that perfect triangular wave. And as you can see, here we have the square wave, here we have the triangular wave. And if I actually zoom in a little further, let's say I go down to 0.1 milliseconds, you can even see the square wave here. It's not a perfect square because there is a certain rise time and a certain fall time, which you have to be cognizant of. At high frequencies, that can cause issues, but as of now, we're pretty all right with this. All right, so this is our square wave. I hope everyone's clear with this. Now I'm going to move on to the triangular wave. In order to do that, I can just, click on the square wave, delete the source, go into the place part menu, which you guys should be comfortable with now, and type VPUL. So that's a pulse waveform. So a pulse waveform gives us the features that we need to simulate a triangular wave. I'm just going to move this here to make it a little cleaner. Okay, this is weird. I'll just place that there. Okay, cool. Don't worry about this black probe. That's just, it's just an anomaly. It's not actually something you need to worry about. All right. So our V1 here can be 1 volt. Excuse me, our V2 here can be -1 volt. We don't want any delay as such. Rise time can be 0.1 M. Fall time can be 0.1 M. And let's say our pulse width is 1 M. And our time period is 2 M. Okay, I'm just trying out these settings. They may not be perfect, but we're just going to run it, see it, and we're going to move forward from there. This sort of iterative testing is something that you guys are going to have to do. All right, so I think I've messed up a little bit here. Okay, so you can see that I have actually ended up creating just another sort of square wave. I'll correct myself in a moment. Yeah, so it's just a sort of a trapezoidal wave, but you can see that we're getting the output that we should be getting. So that's a good thing. Okay, so what I can do is I can make my period 0, my pulse width 0, and my period as well. And then I'm going to run it. Give it a moment. Okay, so this is too much of, okay, I'm just going to reduce this to, let's say, 1 ms. Okay, sorry, I'm facing the same issue we faced earlier. Just give me a second. My rise and fall time, and oh yeah, the period has to be twice of your rise or your fall time. I think we should have it now. There we go, we do have it. So I can just go in and I can reduce the simulation again for, let's say, 10 milliseconds. There you go. We see the input triangular wave. And what we do see as our output is a sinusoidal wave. Obviously, there is a phase shift as we have seen earlier, but we do get a sinusoidal wave. Okay, so now what I can do is I can modify my triangular wave parameters in order to get something slightly different. So let's say I make my rise and fall time 2 milliseconds each, which means that I'm going to have to make my period 4 milliseconds. It has to be double. And I'm just going to click play here. Let's see if we can see any sort of differences in our output. Okay, I'll just reduce this. I can make this fine. Yeah, there we go. So again, we have our triangular wave here and we have a sinusoidal wave. Now what I'm going to do is I'm going to increase the frequency to 0.1 M. Okay, so these are not frequencies, these are time periods, but your frequency is obviously going to be dependent on 1 upon your time period. So you guys can do that calculation accordingly. I'm going to make this 0.2 M. Press play. And yeah, this is a little annoying, but let's just change this slightly to, I think 1 millisecond should be more than enough. Yeah, there we go. So now we're getting a much more representative sine wave because, as we said, as you go to a higher frequency, you get a much more accurate representation of how the integrator works. Because I believe the capacitor goes into short circuit. Please correct me if I'm wrong. The capacitor goes into short circuit and everything passes through. Yeah, everything passes through the capacitor instead of the RF that we've placed up there. The benefits of a practical integrator. And you can see that again here, the capacitor is taking some time to charge up. But once it does, you get a pretty good waveform about your integrator. Yeah, there we go. And again, you can modify this a little. Let's say we just make this 1 volt to -1 volt. Sorry. Yeah. Okay, that is disgusting. Sorry, I'll just make this 2 volts. I'll make this a much better waveform you can see because the charging of the capacitor can be a little annoying to deal with. But here we go. We have our almost perfect triangular waveform and we have our sinusoidal waveform. And we've already seen the frequency response and we have seen the phase response. You guys can feel free to change any of these values. Play around
Rishi,
with it a little.
just
Yes,
a
sir.
second. If you don't want the starting initial part of the waveform where the capacitor is actually charging, you can plot these waveforms in steady state condition. You have that particular option. Once you start digging in, your system will always show you not the initial transient state itself. It will directly show you the steady state. So which means it will discard these first few cycles and it will just basically start off with the steady state cycle. So that's an option. Once you start digging in into your simulation parameters, that is something that should be available to you.
Exactly. And if for now, if you guys don't have the time to dig in, you can just actually change your x-axis and start a few milliseconds after the capacitor is charged up. This is a Jugadu method, it's just helpful to know when you're trying to plot your waveforms.
Yeah.
Okay, so one more thing in Orcad is this is not relevant to our current practical, but it's just something you guys are going to find useful later on, is that we have these bias voltage displays. So I'm just going to click this bias voltage and there we go. So I can see the voltage at different points of the circuit. This is much easier than looking at the simulation plots. You can just look at this. You can take a screenshot, and if so is asking you what is the exact voltage you're getting, you can just show this as well if it's allowed. And you even have the currents. So as we can see here, we have the extremely tiny current going into the op-amp at the inverting and non-inverting terminal. It's literally picoamperes. And that sort of goes in with the entire point that we do not want current flowing into the op-amp, otherwise it can saturate rather easily. And that's why we have this tiny little current going in. And you can even see the watt displays if you want, the wattage displays, but not relevant to us as of now. All right, so this is Orcad for you. And just a few more features that I want to discuss since this is the first session with Orcad. Let's say you want to move the entire circuit somewhere. You can literally select the entire thing and you can move it around. Really convenient. Let's say I want to create a new circuit within the same practice. Let's say I want to do a differentiator within the same practice. I'm going to call it diff. You can see I can do that. It opens up a new page here. I can control A this, control C this, and control V this right here and place it. And then you can make the edits that you need for a differentiator, which I believe Nandinee is going to cover. So I think my time here is up. So I hope I've covered everything. Is there something else that I need to cover on the integrator front? Hello?
Rishi, sorry, I was on another call. Can you
Yes,
go
sir.
ahead, please?
Yes, sir. I was just asking if I have covered everything or is something else required on the
No, no, no.
integrator
As
front
of
on
right now,
OrCAD?
everything that whatever I wanted, everything's been covered. So I think we
Sure, sir.
can uh, complete this at this point. I
Sure, sir.
think differentiator Nandini, because of the fact that they've been at this for 2 hours, I think we can close at this point. We'll
Yes, sir.
start at 8 a.m. tomorrow for the differentiator session. All right, so guys, everyone, just a quick thing. So tomorrow 8 a.m. again we'll start off. So I think we can because I again have a lecture with them at 11:20. So we'll start off tomorrow at 8 a.m. And Nandini would start off with the differentiator, and then Nidhi would continue with the part which we also require in power electronics. Also, Cherry, I have just emailed you the LTspice these models for Diac Triac. Could you just email them to the entire class, please?
Yes, sir.
All right. Okay. So I think for today, Rishi, excellent explanation again
Thank you,
on
sir.
OrCAD. I hope that all of you all have understood this. Again, as he mentioned very clearly, you will never be able to complete with one particular software. All right. So the more softwares you learn, it's going to be extremely quick to shift to any sort of softwares depending on whatsoever you're going to pursue later, right? So it's always better to be adept at any particular software that's thrown at you. Okay, so if you'll can, if you'll have the time, I would always want you to install OrCAD and repeat the experiments that you're doing out over here on LTspice directly on OrCAD. All right, so that's something that again there is no compulsion on this particular thing. It's as I mentioned to you, it's as much as you learn that's going to be the perfect thing for you. All right. So what we'll do is Rishi, Nandini, and Nidhi will close this session at this point. All right, and we'll regroup tomorrow at 8 a.m. again.
All right, sir.
All right.
Yes, sir.
Okay.
Will I be covering differentiator on OrCAD tomorrow, or will it just
Yes.
be an LTspice session?
So no,
Okay,
I think
OrCAD.
differentiator tomorrow. Let's first start off and check how much time Nandini and Nidhi take. All right. Join in if we feel that okay, there is time enough that we can start because tomorrow 9
Sure,
a.m.
sir.
is my session only. All right. So we
Okay.
can continue at that time. So it shouldn't be a problem.
Yes, sir. And tomorrow, actually, OrCAD will take very little time for differentiator because as I
Okay.
show them, I can just copy the entire circuit and just make the small
Sounds
edits
good.
required.
Sounds good. Sounds good. Sounds good.
Okay, sir.
We can do that then. Yeah.
Okay.
All right. All
Thank
right.
you, sir.
Thank you. Thank you very much, everyone. Guys, we'll drop off this call at particular. You all can start off with your 10:10 lecture, and I'll see you guys at 11:20 then. All right. Nidhi, Nandini, and Rishi, thank you again so much for this particular thing. We'll start off immediately at 11:20.
Thank you, sir. Bye.
Thank you, sir.
Bye. Bye, everyone. Bye, everyone. Thank you, everyone.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah. Bye, everyone.
Yes, sir.